graph the following function and its reciprocal. Give the domain and range for both. Give equations for any asymptotes. Here, the original function y equals f of x must be graphed first. In this case, this is a quadratic function that is represented in vertex form. F of x equals a times x minus p all squared plus q. In this case, a, the vertical stretch factor, is equal to 1/2, and p comma q corresponding to the coordinates of the vertex are 0, -2. We then graph the reciprocal function. For each point x, y on the original function, the point x, 1/y is on the reciprocal function. The domain is the set of possible x values, and the range is the set of possible y values. Vertical asymptotes have the form x equals c. Note that these correspond to the x-intercepts of the original function. The horizontal asymptote will always be y equals 0. First of all, let's look at the original function y equals f of x. The vertex at the point 0, -2. And then we have an a value of 1/2. This means that as we go over 1, meaning right 1 or left 1 from the vertex, we would go up by 1/2. From the vertex, if we go over 2, we would go up 2. Over 3 from the vertex, we go up 4.5. And finally, going over 4 from the vertex, we would have to go up 8. We then have our original function. The domain of any quadratic function is going to be x is an element of the set of real numbers. There is no restriction on the values for x. As for the range, we have a parabola opening upwards. In this case, we have a minimum y value of -2, which is the y value of the vertex. The range then will be y greater than or equal to -2, and y is an element of the set of real numbers. Let's now look at the reciprocal of f of x. There are 4 invariant points. Recall that these are points where the y value is either 1 or -1. Here's a point where y equals 1. Here y is -1. Another invariant point with y equal -1. And another one where y equals 1. We then look at the x-intercepts of the original function f of x. Here we have 2 x-intercepts. One of those at x equals -2. This corresponds to a vertical asymptote. And then we have another x-intercept at x equals 2. I will plot 3 additional points by taking the reciprocal of the y values. First of all, for the vertex, which is at the point 0, -2, this then corresponds to the point 0, -1/2 for the reciprocal. Then for the points -4, 6 and 4, 6 on the original function, these correspond to -4, 1/6 and 4, 1/6 on the reciprocal function. We then connect the points for the reciprocal function. Here we have 3 different segments separated by the 2 vertical asymptotes. To the left of the first asymptote at x equals -2, making sure that we go through all of the points and that we approach the vertical asymptote. Then we have the segment in between the two vertical asymptotes. This time the y values are negative, so this will be below the x-axis. And finally, to the right of the second vertical asymptote at x equals 2, again making sure we go through the points and approaching the vertical asymptote. In this case, all of the y values will be positive. Note that as x gets infinitely large or infinitely small for the original functions, the reciprocal function must approach 0. This corresponds to the horizontal asymptote of y equals 0, corresponding to the x-axis. As for the domain and range for the reciprocal function, for the domain, the possible x values, x cannot be -2 and 2. These correspond to the vertical asymptotes. And x is an element of the set of real numbers. As for the range, the possible y values, notice the portion between the two asymptotes. This is the portion of the graph below the x-axis. The y value reaches a maximum value there of -1/2. We therefore have y less than or equal to -1/2. For the other portions of the graph, where we have it approaching the x-axis, we have y greater than 0, and y is an element of the set of real numbers. As for the asymptotes, we have two vertical asymptotes. One, the equation is x equals -2. The other one, x equals 2. And we have a horizontal asymptote with the equation y equals 0.